Welcome to Miscellaneous Topics, Part 2. Today, we are going to be modeling the universe. So I want you to finish reading through this on your own, and you're going to answer the rest of the questions for homework. So I'm going to give you a few tips now, but you need to go back and read through it, everything. Okay, so we have galaxies here, and we are drawing a Gaussian surface. And we can use the Gaussian surface not only for the electric field, but for the gravitational field as well, or for the gravitational force, which is just multiplying the field by m. So if you have a uniform sphere, let's treat the Earth as a uniform sphere, and you dig a hole, you're standing in the hole here, the gravitational force that you feel is just from the mass that's enclosed by a sphere of radius r, where r is your distance from the center of the Earth. So all the mass that's out here, the net force of all the mass in this outer shell here on you is 0. So you can just look at the force from the mass that's enclosed. Okay, so here we're looking for the total energy in the enclosed region, and we have kinetic energy, which is 1/2 mv squared, and we have gravitational potential energy. So this is the kinetic energy, and this is the gravitational potential energy. We recognize the kinetic energy here. This mass is the mass that's enclosed by our Gaussian surface. For the gravitational potential energy, we cannot just say mgh unless we're staying near sea level. So if we can't say this, then what we have to do is say the force of gravity is equal to capital G times m times little m over r squared, and this is acting inward, so let's say in the negative r hat direction. Okay, so acting inward towards the center of the sphere. Then we can find the work by doing the integral of the dot product with the vector dr. And we're going to start from infinity, and we're going to say at infinity, the gravitational potential energy is 0, and then we're going to come in from infinity to a distance, little r. When I do the dot product, the force of gravity is pointing inward, but the vector dr is pointing in the positive direction for r, so I get a negative sign from doing the dot product. And this is similar to when we calculated the electric potential back in Physics 261. Okay, and then I put this in here, so I have G capital M little m over, let's call it little r squared, since I'm integrating with respect to little r. Okay, and then I can do my integration, and when I integrate 1 over r squared, I get negative 1 over r. So this was negative, so now it's positive. And when I put in the limits of integration, I'm going from infinity to r. When I put infinity in the denominator, it goes to 0, so this is just over r. This is the work done by the force of gravity as you come in from infinity and go to little r. But remember, the work is equal to the negative change in gravitational potential energy. So this is minus GE final plus GE initial, but I started at infinity, and I'm going to say at infinity, that's my reference point where the gravitational potential energy is equal to 0. So my final gravitational potential energy is negative G capital M little m over R, which is what I have there. Okay, so I want you to read through all of this, and then we have equation number 2, which says that the velocity of a galaxy at a distance r away from the point where you are making your observations, the velocity is equal to a constant times that distance. But it's not really a constant, it actually depends on time. So this capital H is Hubble's constant, but it changes with time. Okay, and then we take equation 1 and equation 2. We put the velocity HR in for velocity here, and we get equation 3. Okay, then you can read through all of this. So we made, we have the density here. This is the mass density. The mass density is the mass over the volume for our Gaussian sphere here, which has a radius of capital R, is 4/3 pi r cubed. So we put that in our equation here for m over r. So solve this for m over r and put it into equation 3, and we get this, which simplifies to what we have here. Okay, E is a constant, little m is a constant, and 2. And so we're going to lump these constants together, and we're going to define those constants as a product of 2 different constants. So we're going to say let minus k times c squared be equal to 2 times E over m. So these are all constants here. So c squared is chosen so that k is either equal to 1, 0, or negative 1. This constant k tells you something about the curvature of the universe. If k is equal to 1, the curvature is positive and space has a spherical shape. This requires E to be negative. K is equal to negative 1, the curvature is negative and space has a hyperbolic shape. This requires the energy to be positive. And if k is equal to 0, the universe has a flat Euclidean shape. This requires the universe to have no net energy, and the expansion of the universe asymptotically approaches 0 velocity as r approaches infinity. Okay, so then making this definition and putting it into our equation back here, we get this form of our equation, and then we bring the h squared r squared, well, we leave the hr squared r squared on this side and bring this term over here. And then from equation 2 we have hr is equal to dr dt, so we put that in here. And our constant c here turns out to be everybody's favorite constant in relativity, the speed of light, little c. And so we get this equation, which is the first Friedmann equation, or the velocity equation, and then we move on to part 2. So in part 2, we're going to do the integral here. We have a force, pressure is equal to force over area, so we can say force is equal to pressure times area. Area times dx is equal to dv, so that's like, if you have the area here and this distance here is dx, then that is equal to a small volume dv. Okay, so then we get equation 4 here and equation 5 here, and now we're using the energy density. So somewhere it told us, and I don't remember where, but you'll find it when you read through, that we are going to be using the energy density instead of the mass density, so the energy density would be energy divided by 4/3 pi r cubed. Okay, so then we have equation 4 here. It's equation 4. We're going to put equation 5 in. Then we're going to take the derivative on the left-hand side using the chain rule and simplify, and we get this equation, which is called the cosmological work energy relationship. Okay, then you're going to read through here, and if we take a time derivative of the first Friedmann equation, we get this, and we have this term here, and we have an equation up here. So we can use the cosmological work energy relationship to replace the r d rho dt that we have here. And we get this, then we simplify. We have a 8/3 pi gr negative 3 times rho here, and 8/3 pi gr 2 times rho here, so that gives us 8/3 pi gr negative rho. And then we have this minus 3 times p here. P is the pressure, rho is the energy density. Make sure you keep those straight. This is the second Friedmann equation, or the acceleration equation. So our first Friedmann equation that had a dr dt, which was the velocity, that's going back to what we had here. Velocity is dr dt. And then we have second derivative here, that would be the acceleration. Okay, then read through this, and in our next video we'll pick up with part 3. Before you move on to the next video, if you haven't done so already, I'd like you to read through everything in part 1 and part 2.